All right, welcome ladies and gentlemen. This is video number 1 in our gases unit, so you want to make sure you have your note page open where it says video number 1. This video is about something called kinetic molecular theory, so we'll be talking about what is this thing and the components of it. So first up, what is kinetic molecular theory? It's a model, so that means a description, essentially, that predicts the behavior of ideal gas molecules. Well, what do I mean when I say behavior? It's essentially, when we talk about the behavior of gases, which is a pretty common term, we're talking about conditions. So things like, hey, what happens if you change pressure? Hey, what's caused pressure? What about volume? What's the effect the temperature has on gases? What about the velocity of the gas? The frequency of the collisions that a gas experiences, force of collisions. That's what we mean when we say behavior of gases, these sort of sets of conditions and how the gas particles move, what they do. There are many what are called postulates of kinetic molecular theory, which you'll see me abbreviate a lot as KMT. And a postulate is simply a statement. It's a sentence. It says, okay, this thing happens. So those are the postulates of kinetic molecular theory, and they're predicting how gases behave. So the first statement, the first postulate of kinetic molecular theory, are that gas particles are always in random straight line motion. So gas particles, they don't go around in circles like that. No, that's not what they do. They move like that. And they're constantly moving, and it's random. So one particle might be going like this, another might be going like this, another might be going like this, etc., etc. The next statement is that gas particles collide with each other and the walls of their container. This issue of collision, which again means things hitting one another, if you think of like a car collision, these collisions with the walls of the container, it's only the walls of the container, but these are the collisions that create pressure. So when a gas particle collides with the walls of the container, that's what's actually creating the pressure that we're reading. So pressure, I mean, it's that particles hitting the insides of its container. And furthermore, these collisions that gas particles experience, they are what are called elastic collisions. What does that mean? There is no loss of energy. When the gas particles collide with one another, they don't actually lose any energy. So they don't slow down and they don't speed up. When they hit one another, they just bounce off and keep going in the opposite direction without speeding down or slowing up. So it's not, car collisions are not elastic because when cars collide, they stop. And so that means that they lost all their energy that they had going into the collision. Gas particles are the opposite of that. When they collide, they actually don't lose any energy. The reason they don't lose energy is transferred from one colliding particle to the other colliding particle. And so that energy gets completely transferred. We don't lose anything. The next statement of kinetic molecular theory is that gas particles have no intermolecular forces of attraction, so IMFs. Remember this idea of stickiness. IMFs are stickiness. How much does one molecule stick to another? And gas particles don't stick to one another. So that's what this is saying. Gas particles aren't sticky. And another way of saying that is this last bit right here. They don't attract or repel one another. So they're not attracted to one another, they're not sticking to one another, but they're also not repelled or repulsed by one another. And then number 4, gas particles have mass but no volume. So this is really kind of a big one, this last one right here. Gas particles are considered to have no volume. And the gas particles are very far apart from one another. If you think about a room and the amount of gas that's in the room, there's a ton of empty space between the gas particles because the gas particles are simply so far away. And we say that relative to their very small size, gas particles have volume that is negligible. You'll see this term used a lot, negligible. That means essentially zero. It means almost nothing, basically zero. So this is an assumption that gas particles essentially have zero volume. And we're going to talk about that in a second because that shouldn't really make too much sense to you. Next is that the fifth statement is the absolute temperature. So temperature in the Kelvin scale. In the Kelvin scale only. It doesn't work in Celsius or Fahrenheit. The absolute temperature in the Kelvin scale for an ideal gas is directly proportional to the average kinetic energy of that gas particle. So essentially what this is saying is as your temperature increases, the average kinetic energy of your gas particle also increases. This should make sense because this is essentially talking about how fast the gas particles are moving. And this is saying if you increase the temperature, the gas particles speed up. That should make sense. You've seen this before, right? Solids, they move very, very slowly. They basically don't move around. They kind of vibrate in place. Liquids move a little bit more, but they're still relatively slow, whereas gas particles move fast. And the more temperature the more you increase the temperature of the gas system, the more energy the gas particles are going to have, the faster they're going to be moving. That's what this last statement is saying. Now, a final note on kinetic molecular theory. Kinetic molecular theory describes ideal gases. Well, what does ideal mean? Ideal means absolutely perfect. Ideal means it's like this golden thing, but the thing is, ideal doesn't actually exist. There is no such thing as perfect. It doesn't actually exist in the real world. So ideal gases are absolutely perfect, and they follow the kinetic molecular theory completely. But ideal gases don't actually exist. And especially if you consider that volume statement that ideal gases occupy zero volume, they don't have a volume, well, that cannot be true. There's nothing out there that doesn't occupy volume. So this is kind of saying, hey, these are perfect gases, but they don't actually exist. Real gases, and I'm going to come back to that in a sec. Real gases can behave like ideal gases, can get close to ideal gas behavior. They won't follow it exactly, but they get close. And it's sort of like kinetic molecular theory is sort of a close enough. A lot of gases follow this pretty well, which is why we use it. And we will be discussing how real gases deviate or alter from kinetic molecular theory, and why, because basically kinetic molecular theory is not perfect. All right, so this wraps up video number 1 in our gases unit on kinetic molecular theory.